There we go. Now I'm recording. Um, okay, so we're going to jump into wrap up chapter number 7. The PowerPoint and PDF I'm saving right now. You can access those. And I gotta get go full screen on this stuff, and then we are. Let's see, there we go. Da, 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 da. Share my screen. Okay, so we are talking about ideal gases. Monday was a pretty heavy lift because on Monday we were talking about relationships between two variables. We were talking about, well, if the pressure changes, what happens to the volume? If the temperature changes, what happens to the volume? We're talking about all these limited, or we're kind of giving a limited scope on everything. Today, what we're going to be doing is we're talking about ideal gases. And what that means is not so much like, are we talking about a special type of gas? But instead, what we can do is we can operate under the idea that most gases are going to behave as ideal gases. So, what that means is we are going to be combining pressure, volume, number or amount, and temperature. We're going to be combining all these different things, and we'll be able to do calculations based on that. So we'll be talking about in the event that the pressure is this, and the pressure is this, the volume is this, and the temperature is this, how much gas is present there? So that's one of the key parts about ideal gases. And for that, we're going to use what's known as the ideal gas law or the ideal gas equation. And we're going to be talking about the combined gas law. So those are two big calculations that you'll need today. Now, I'm going to pull my chat window up, scroll that, move that over here, move the poll questions right over there. And we're going to go ahead and get started with our first poll question. Okay, so um, how do the particles, remember all these blue balls were those gas particles, um, how do they behave? No, 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 stop, end poll. That's not the one that I wanted because it has 4 different options, and that's not what I'm looking for. Instead, I'm looking for, nope, this one. Launch, there we go. If you were to add heat, so we've got our gas in a enclosed container, are the particles going to move faster? A. B, the particles are going to move slower, or C, the particle speed is not going to change. And just to kind of illustrate this a little bit more, we can look at this model right here. This is a model where we adjusted the heat. And what did you observe? We adjusted the space that that container was in. What were we observing there? And I'm going to give another 10 seconds or so for folks to respond to that. I'll jump back and I'm going to go ahead and call it right there. That looks good. So how do the particles behave when this gas is heated? The particles are going to move faster. Those individual blue balls are going to be moving faster. So what that's going to mean is, or here, add to the chat, kind of a continuation. I'll share the results, but add to the chat, what is going to happen to, and I would like you to respond with U for up or D for down. What is going to happen to the number of collisions? And that's collisions between individual gas particles, as well as collisions between the particles and the walls. And I'm getting nothing but U's, nothing but ups. As we increase the temperature, the number of collisions is going to increase. So too is the speed. So the speed of those particles is going to increase. Great job, everyone. Awesome. Okay. Now, this was a little model that we played with the other day. This is on that PHET, PHET web page that we've used a couple of times to show some examples. Now, those relationships that we kind of looked at, or all of those four different relationships that we looked at, we had Boyles's law, Charles's law, the Gay-Lussac law, and Avogadro's law. It's important that you know what law defines what relationship. So this is Boyle's, Charles, Gay-Lussac, and last but not least, and I kind of think that this is it's the simplest one for me to remember because anytime I see that N, my mind goes to, okay, that's number of moles. And whenever I'm talking about number of moles, I'm talking about Avogadro. Amadeo Avogadro. So the or Boyles's law, Charles's law, Gay-Lussac law, and Avogadro's law. Now, one of the things that we talked about the other day with respect to these different laws was the relationship, the type of relationship. If you notice, all of these bottom three, when the volume goes up, um, or sorry, if the temperature goes up, volume goes up. If the temperature goes up, pressure goes up. If the number of moles goes up, then the volume is going to go up. In the event that you flipped it and you saw the temperature go down, well, what would happen to the volume when we're talking about Charles's law? Well, then your volume is going to go down. These are directly related, and the other is indirectly. So, what I want you to be able to do with all of this, though, most importantly, is I want you to be able to identify if I gave you the equation, I want you to say, aha, that's Boyle's law. Okay. So that expect that as a test question. Now, what we're getting into today, and this is a part of one of your quizzes as well as one of your activities. What if you change more than one variable? So, what I mean by that is, what if you heat something and you shrink the container that it's in? Well, ask yourself the simple question. And whenever I say simple, I mean we're looking for a very binary answer. Is it going to change? Yes or no? Is something about that gas going to change if we both decrease the volume and we increase the temperature? Yes. Something is going to change. Now, the combined gas law is the law that we can use to address this sort of thing and do this sort of calculation to come up with an answer. So, when we're doing this sort of calculation, we've got kind of an initial situation and then a final. Anytime we're doing a calculation like this, your temperature needs to be in kelvins. Could anyone add to the chat the unit for, okay, so temperature is going to be in kelvins. What about volume? What are the units for volume? Liters, exactly right. I got a private message that I'm responding to real quick. So I understand all the books. Um, so there we go. So volume is going to be in liters. That's absolutely right. I'm going to go ahead and keep track of these. T Kelvin. V is going to be in liters. Now, with that in mind, um, if you were presented with a question that listed the volume in milliliters, could you do that calculation? Yeah, you'd have to convert it from liters to, from milliliters to liters. The calculation can still be done, but we need to keep in mind that anytime you're doing this sort of thing, you need to be working in liters. Okay. Now, what about our units for pressure? Could anyone add those to the chat? Great job, Emily and Adriana. Atmospheres, ATM. Now, if you see, you might see something that's pascals or kilopascals, but that's not the one that we're using. We're going to be strictly using atmospheres. Okay. Now, on the next page, let's go ahead and do a practice problem. So we're going to practice using the combined gas law. P1V1 over T1 is equal to P2V2 over T2. A balloon filled with helium gas. Now, before we proceed from here, would this question be different if I had, let's say, nitrogen gas? Add a Y for yes, it'd be different, or N, no, the calculation would effectively be the same. It's the same. You're absolutely right. Because the important part about this is that the identity of the gas does not matter. So, helium, and this is, I'm going to use one of my favorite words, superfluous. I love that word because it's kind of just saying, like, well, it's unnecessary. But this right here, this identifying the gas, that's superfluous information. Now, can everyone say it with me? One, two, three, superfluous. Great, great. Now, this is unnecessary information, but we'll proceed. So, a balloon filled with gas, I'm just going to say, has a volume of 22.4 liters at 1 atmosphere and 0 degrees Celsius. Oh, crap. I mean, excuse my language. What happens if I plug 0 in here? What's that going to mean? Multiply or divide anything by 0, and ooh, you're not going to get a number, are you? So, how do I address that? Well, I think what I'm going to do is Triana, dang. Yep, you're absolutely right. 273 Kelvin. Okay, so this is setting the stage for what's going on. 22.4, or actually 1 atmosphere, 22.4, and 273 Kelvin. Okay, great. Now we got two situations. One situation is what's the volume of the balloon at 2 atmospheres? So that's our P2 and negative 50 degrees Celsius. This is our T2. Well, it's close to our T2. We've got to add 273 to that, which is going to give us 223 Kelvin. Could everyone who's good with that T2 add to the chat Y or N if you're not good with it? Okay. So I'm going to set all this up. We've got one, I'm going to go with example A, 1 atmosphere times 22.4 liters divided by 273 Kelvin. Okay, is everyone good with that? I'm going to count to three. One, two, three. Good. Now what I'm going to do is I'm going to set this equal to, well, all of what I've got on the other side. I've got a pressure of 2 atmospheres, 2 atm. Then I've got V2. That's what we're solving for. And then last but not least, I've got my temperature of 223 Kelvin. Okay, so now I'm going to do the calculation. The way that I'm going to do the calculation is I'm going to do the left-hand side, which I've got to pull up my phone, calculator. Boop, 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 boop. Oh, look, everyone. My calculator is in the exact same format that it was the other day. Let's see. I'm sure that I could just change that somehow, but I'm not going to. Why? Because I'm stubborn. 22.4 divided by 273. I did that just because 22.4 times 1 is, lo and behold, 22.4. So 22.4 divided by 273 gives me, and this is where the race begins, 0.08205. Oh, dang. Mode. One of your classmates is very thoughtful and told me how to do this. So thank you very much. But wait, this is my phone. I don't see him. Okay. Again, I'm stubborn. Okay, so now what I'm going to do is I'm going to multiply. So this is equal to 2. I'm going to throw in parentheses V2 over 223 Kelvin. Multiply each side by 223 because I want to get rid of this. Done. Done. Thank you. Stubbornness unite. Stubbornness and procrastination is a very bad combination, and I'm very good at having both of them. Oh, and a nice layer of ADHD. And man, oh man, it is fun having a clean work area. Okay, sorry. That's just my little aside there. Okay, so now what I'm going to do is I'm going to take this 0.08205. I left it in the calculator because I didn't want to round anything. I'm going to multiply that by 223. And I'm going to get my volume, V2. I'm writing over that balloon just because, well, the color is contrasting it. I got, oh, dang. I'm actually not solving for V2 quite yet because one of your classmates, Emily, beat me to the punch. You're absolutely right. It's 18.29 equals 2V2 divide by 2. Dang, Emily. If you're thinking the exact same thing that I am of, we don't really need you, Dr. Gray, or Joel, whatever you call me, I respect that. V2 is 9.15. You're absolutely right. Emily, you don't need to apologize for that. Okay. Did anyone and everyone get that? And we got some yes, or we got one yes, and Emily's obviously yes. We got another yes. So essentially what happens here is we've got a balloon. It's filled up with 22.4 liters of a gas. It's at 0 degrees Celsius. We increase the pressure. So what happens when we increase the pressure? What happens to the volume typically? Well, you increase the pressure, the volume's going to go down. Whose law kind of dictates that? So what I'm doing is I'm dissecting this and thinking about it one by one. If we increase the pressure, what do we expect the volume to do? We expect the volume to go down. Okay? Boyle's law says that. So that's Boyle's law is the relationship between pressure and volume, but we're talking about another thing here. What happens when we drop the temperature? When we drop the temperature from 0 degrees Celsius to negative 50 degrees Celsius. So when you chill something, when you bring the temperature down, what do you expect the volume to do? We'll go back and look at, well, when the temperature goes down, we would expect from Charles's law the volume to go down as well. So essentially, this right here, we're taking two approaches to do the same thing. We are, or we're, sorry, there are two variables that are changing, temperature and pressure. And they're both directing towards the volume of our container shrinking. Now, did the volume of our container shrink? Yeah, it went from 22.4 liters to 9.15 liters. Okay, can I get a Y in the chat if you understand that we are observing both Boyle's and Charles's law take place? And you understand kind of what's happening here. Okay. Okay, wonderful. Now, let's just look at the next thing. The next problem, what does it say? What is the volume of the balloon at 2 atmospheres? And, oh, our temperature is 50 degrees Celsius. So I would like you to respond with D or U. What is, so I'm going to scribble out, just ignore the calculation that we just did. I'm going to scribble out A. I'm going to change the temperature. Our T2 is going to be 323 Kelvin. So now what our scenario is looking at this and how it's impacted by these variables. So the first question that I've got, and I'd like you to respond in the chat, how will our, or what is happening to our pressure? Is it going down or is it going up? Our pressure is going from 1 atmosphere to 2 atmospheres. We're just looking at B. Okay, so it's going up. Okay, great. Now, if our pressure is going up, now what I'd like you to do for this next response is what do you expect the volume to do? Is the volume going to go D down or is it going to go U up based on only the pressure change? Our pressure went up from 1 to 2 atmospheres. So what do we expect our volume to do? And just so we're ignoring this part for the time being, we're ignoring the temperature change. When our pressure goes up, we expect our volume to go down. That's right. Okay. Now let's isolate and think about just generally when you heat a container or when you heat a gas, what does the volume do? Does the volume go up or down? Yeah, the volume's going to go up. So essentially, we've got two competing things. And the question is, what has a greater impact? Is the greater impact observed because the pressure went up, or is it because the temperature went up? Because the pressure going up will cause the volume to go down. The temperature going up will cause the volume to go up. Could I get a Y or an N in the chat if you follow that we've got two competing things going on? Okay. Okay, now we're going to go ahead and tackle this calculation. B. The great thing about this calculation is look at the calculation A. That's all describing our initial situation. So that's all the exact same. So that's 1 atmosphere, 22.4 liters, 273 K. That's equal to 2 atmospheres, V2, over. Now here, our T2 is different. It's now 323 K. Okay, so we don't have to plug in the calculation because, well, I'm going to plug in the calculation actually. Sorry, I lied to you guys. 22.4 divided by 22.4 divided by 273. And that is going to be equal to 0.08205 equals. Well, that, I'm going to multiply each side by 323. And whenever anyone has the answer, I'm looking at my chat for Emily's name to pop up with the correct answer. But anyone else is welcome as well. 2 atmospheres, I've got this 0.08205 times 323, and I'm going to divide that by 2. Lazaro, absolutely right. And that is V2 equals 13.25 liters. Okay. So what happened? Well, our temperature went up, our pressure went up, our volume, well, it dropped. Did it drop as much as whenever we were cooling this system as well? It didn't. But that kind of makes sense. It's almost like what we see is one step forward with the pressure change, and then one step backward, or two steps backwards, I guess. I don't know. Two steps forward. It's like we went in this direction and then we went in this direction to offset it when our temperature changed. Okay. Can I get a Y in the chat if you also got this calculation or this 13.25? And if you didn't do the calculation, but you followed it along and followed the setup and you're good with that, add a Y. Wonderful. And just so you guys know, if ever I call anyone's name out and say, you've been answering questions, I don't want you to feel like I'm putting any pressure on you. I appreciate when you guys are contributing. It's really awesome. Okay. So it looks like we're good on this. And as always happens, I had a moment where I thought, oh no, am I recording? And yes, I am recording. So we're good there. This is a good calculation that you should be able to do. Now, the next heavy lift for this class or for this module is not the combined gas law, but what's known as the ideal gas law. The ideal gas law asks you, what if you don't know all of the variables? Or what if you know all of them except one? Can you answer this sort of question? And the answer is yes. If you remember at the very beginning of this presentation, I showed this. I said ideal gases were interested in pressure, volume, number, or amount, and temperature. P, V, and T, even though it does kind of look like, just because of my, I'll say, creative interpretation of handwriting, it does kind of look like I wrote punt. So it could be that if somebody's joining class late, they think, oh, clearly he's mentioning punting. This must be like a Tom Brady deflate gate situation because it also mentions ideal gases. Um, no, that's a V. So P, V, N, and T. Well, those are the variables that we know about. This is another variable. This R value, this capital R, that is a value that I will provide to you. The units for R are, sorry about that, liters times atmospheres times moles times Kelvin. Just as a little bit of a suggestion and hint, if I ask you on your exam, what are the units for pressure that we use? Let's say this is a test question. You get A, kPa, B, PA, C, PSI, D, KSI. I think he's a YouTuber. And E, atmospheres. If you see that question and think, oh no, I think that it's kilopascals, so I think it's A. Or ooh. But I've seen PSI. I know PSI. That's on my car tires. That's on my bike tires. That's on a football. Got it. It's PSI. I'm done. If ever you see that question and you're flustered and you're not sure what to put, this number right here will be on your exam along with the units. Use that. Because do the units here, so this is a molecule, not molecule, this is a number that the units are multiple different dimensions. We're taking into consideration the volume, liters. We're taking into consideration the temperature, Kelvin, moles, and the amount, and last but not least, atmospheres. So if ever you see that question, look around and remember, oh yeah, the R value is the what's known as ideal gas constant. Aha! It's got to be E because that is mentioned in my gas constant value. Okay, that R value, you do not have to memorize that. That will be included on your exam and any questions where it is needed. Um, so yeah, just be ready to go with that. Um, if you do a Google search for what's the R value, you're going to be given something that's different from this. The reason for that is because an R value or the R value has a number of different forms and a number of different sorts of calculations that chemists use on a regular basis. So if you see that, there's one that you might see is like 8.3145. Don't get confused and say, oh, that's the one that I need to use. I will give you this number. Use the number that I give you because that's the number that I use to do the calculations. Okay, now the ideal gas equation is PV is equal to nRT. What that means is that the pressure times the volume is equal to the amount of a gas times the R value times temperature. Now, if I were to say, I'm going to give you the pressure of a gas, I'm going to give you the number of moles of a gas, and I'm going to give you the temperature of a gas. Would you be able to figure out or do the algebra? And I'm sorry for saying algebra. Some people don't like that word. Would you be able to do the calculation or rearrange this equation where you only have volume on one side, or you have volume on a side by itself? What that would look like, I asked a yes or no question. I got some yeses there. That would look like this. Divide each side by P. The left-hand side, when we divide PV by P, P is gone. When we divide the right-hand side by P, well, it stays because it's not going to cancel out. So then this equation ends up looking like this. V equals nRT over P. Done. So being able to do that is an important part of using this calculation or using this equation. I will give you PV equals nRT. I will give you the R value. You just need to be able to interpret the question that you're given and be able to modify the units or modify the numbers that you're given to reflect what you need. So a fair question is, well, what's the difference between these? Well, the ideal gas law, you're going to use that when you're given the amount of a gas. The pressure must be listed in atmospheres, and there's the equation. The combined gas law, well, that is when the conditions change, not when the amount of gas changes. In both laws, you're going to use your temperature measured in kelvins. Now, let's go ahead and tackle this question right here. Which of these problems requires using the ideal gas law? A balloon filled with helium gas. Okay, so we're given the identity of our gas. I'm going to scribble this out though. Has a volume of 22.4 liters, 1 atmosphere, 0 degrees Celsius. What is the volume of the balloon at 2 atmospheres and 50 degrees Celsius? Add to the chat Y or N. Are you going to use the ideal gas equation for this? Let's just go ahead. I've got a strong N. Got my volume, got my pressure, I got my temperature, got my pressure, I've got my temperature, and I'm asked for my volume. I was just asked to go back a slide. Absolutely. Absolutely. So you use the combined gas law whenever the number of moles are basically going to be constant or when the amount is given. Now, when things change, that's when you're going to use the combined gas law. So my question of for option A, are we going to use the ideal gas law? Folks said no. We're absolutely not. Because yeah, it identifies the gas, but it doesn't tell us how much of that gas there is. Now, option B. Option B tells us what pressure, or asks us, what pressure is exerted by zero point 0.5 moles of gas in a 10-liter container at 25 degrees Celsius. There, what are we given? We're given the amount of the gas. Now, let me just dissect this question for a little bit longer. This question is one that folks might see and be like, oh, snap, I need more information. And the reason that they say that is because they look at it and it says zero point 0.5 moles of a gas. Oh, but it doesn't say helium. It doesn't say hydrogen. Again, we don't need to know the identity of gas. We don't care about that. That's one variable. So by telling us the amount of the gas, we know we're going to be using the ideal gas equation. Another thing is question B, answer with a Y or an N in the chat, is question B asking us about a change? No, it's not at all. What pressure is exerted? It doesn't say what pressure is exerted after this, and this has happened. It just says what's the pressure. So a fair question then is, well, let's answer this one. We're going to set up with PV equals nRT. Now, before I go ahead and plug numbers in, I'm going to ask myself, do I need to change the units for moles, for the amount? And I'm going to define everything. Actually, I'm going to reorganize this. PV equals nRT. N is my number of moles. I don't need to change that. 0.5 moles. V is my next unit or my next variable that's provided. 10 liters. Do I need to change that at all? I don't. Last but not least is T, which is 25 degrees Celsius. What is the temperature that I need to use? Exactly, 298 Kelvin. I've also got the R value, which again, my R value would be provided in the question, and the R value is 0.0, I forgot, 821. 0.0821 liters, atmospheres, moles, Kelvin. Okay. What do I want? I want to figure out the pressure. So how do I rearrange this equation? I divide each side by P. The left-hand side. Oh, that's not what I do. Sorry about that. I divide each side by volume. Volume's going to done. Okay. Now, just to sort of double down on the value of knowing the units for R, let's walk through this calculation. Or actually, Lisa, well done. Well done. Great job. Okay. But I want to go ahead and plug this in. P equals 0.5 moles. Okay. Next is R, which is 0.0821. I'm going to write my units. Liters times atmospheres divided by moles Kelvin. times 298. Okay. Divide all of that by 10 liters. Okay. Can I get a Y or an N? Y in the chat if you follow and you're good. Okay. Excellent. Now, before I plug the numbers in, I always like to look and see, okay, well, I've got moles. Units of moles times, well, where are the moles here? They're in the denominator. Cancel, cancel. I'm going to scribble it out. I'm going to done. Now I've got moles or units here are temperature, Kelvin. Kelvin times Kelvin in the denominator, erase, gone. Then I've got liters divided by liters. Liters, liters. Those will cancel out. I see all of the units on the right-hand side of the equation except for atmospheres, which means my answer is going to be in atmospheres. And I'm trusting Lisa's number of 12.2. What did we get? 12.2, 12.24? 12.24 are units, are atmospheres. Can I get a Y in the chat if you follow that sort of calculation? Okay. Now, with that sort of calculation, how can it be made a little bit trickier? How can it be made more complicated? Just so you guys anticipate this, rather than moles, 22.9 grams of O2. My question for you guys, yes or no, could you do this sort of calculation if you had a periodic table before you? Yeah. All that you're doing is you're taking your number of grams of O2 and converting it to number of moles of O2. It's just one additional step. I was going to also add, well, what if the temperature is in degrees Celsius? That already is. I would kind of expect, okay, I'm going to have to do one additional step, whether that's change the temperature or change the grams to moles. There's going to be one more thing. Okay, do we have to round the decimal on the answer? Um, Chances are your answer options, it's going to be something like, well, it's going to be fairly apparent which is the right answer. If you've arrived at 12.2, I might have an answer that's 12. Okay, I see. Divide by 10. Okay. I'm confined. Oh, okay. So somebody sent me a private message that looks like P, we needed to, let's see. Clear, clear, clear. Point 0.5 times point 0.5 times 0.0821 times 298. Okay, that 12.24, we need to divide that by 10. Thank you very much, a classmate sent that in. We need to also, so when we divide by 10, that gets it down to 1.224. Your answer options would be, here, I'll give you multiple choice answer options. C, D. A would be 12.2. Um, B would be 1.224. C would be something like, let's see, 10 divided by. I'm coming up with alternative answer options here. Times 1.026. And then that would be something like 10.26. So your answer options would be like these last two. I got those by not changing the temperature from uh, degrees Celsius. So there'd be some sort of error like that that's taken into consideration. Like if you if you took the wrong fork in the road or if you took a wrong turn at the fork in the road. Okay, on a scale of 1 to 3, 3 being, I feel good about this, 1 being, ooh, I'm in the woods on this one. Um, Respond in the chat and you can do a private message. How do you feel about ideal gas law equations? Okay, above 2 is good because that sounds to me like you do the activities, or 2 and above, I think is good. 2, 3 with practice, I like it. Okay, okay. Now, same question, but about combined gas law questions. Where do you feel on that? 1, I'm in the woods. 3, I feel good. Okay. Well, then I think what we should do is let me go ahead, go back to the PowerPoint file, and I'm going to add question. I'm going to add a blank slide. We're going to do a practice problem. Okay. So I'm going to work through this. And actually, you know what I'm going to say is if you're good, or if you just, you'd like to watch this later on, by all means, hope you have a great day. I'm going to continue recording this. I'm going to go through one ideal gas law equation, and then I'm going to go through one combined gas law equation practice problem. But if you're good, I hope you have a great Wednesday. I'll see you on Monday. If you want to hang around, ask questions, anything like that, hang around. I'll be here. So here's our question. We have, let's say, 13.6 grams of CH4 in 575 milliliters, or in a 575 milliliter container with pressure of 1.2 atmospheres and temp of 398 Kelvin. Now, my first question here is, are we going to be doing the ideal gas equation or the combined gas law equation? Well, this gives us an amount of a gas. So we are going to be using the ideal gas equation because, and I'm going to add in here CH4 gas. We've got an amount of a gas. It's a mass. So what we need to do is first look at our equation. PV equals nRT. R equals, and this again would be on the equation, 821 liters, atmospheres, moles over moles Kelvin. Okay. I like to put all my variables out here. P, V, N, R, T. And you know what I did? Wait. Sorry. I'm I'm changing this because I realized that I defined everything. Um, so I'm going to say I've got N right here, my volume, my pressure, what I need to go at what temp is this possible? So T is what I need. Okay. Sorry about that, everyone. So we've got our pressure, 1.2 atmospheres. I don't need to change that because that's good. I don't need to change my units, which pretty standard. I kind of told you guys that you wouldn't expect that. You shouldn't expect to do that. 575 milliliters. Okay, that's one that we haven't talked about too much, but it is a unit conversion. If anyone remembers, there was 1,000 milliliters in 1 liter. Well, to convert from milliliters to liters, and this is kind of the extent of the volume conversions that you should expect to see or could see. This is 0.575 liters. So I'm going to put a check mark by that. I'm going to put a check mark by that. So I've got pressure and volume. N is my gas. And actually, I'm going to pause for a second. If anyone's unsure about what I've done so far, you can send me a private message or a group message. Okay. Now, N is 13.6 grams. That's what I've got. You know what I want to do is I want to go ahead and bypass that for a second, just so I can get more of a definition of everything that I've got. 0.0821 is my R value. My T is unsure. So the reason that I did all of that is because what I like to do is I like to take my equation and say, what do I not know? And what do I need to solve for? I need to solve for T. So what that means I need to do is I need to get T by itself. How do I do that? Well, I divide each side by N and R. When I divide the right-hand side by N and R, I get rid of it. When I divide the left-hand side, PV over NR, that stays there. So I'm left with temperature. Now what I'm going to do is start filling in values. 1.2 times 0.575. That 0.575 was the conversion from milliliters to liters. N. I waited long enough. I need to convert 13.6 grams of CH4 to moles. Well, 13.6 grams. When you look at the periodic table, you'll see that carbon is 12 grams per mole. Hydrogen is 1 gram per mole. So with their powers combined, they end up with 4 hydrogens, which is 4 plus 12, which is 16 grams per mole. So that's 16 grams, and then up top, I'm going to write 1 mole. So my answer, or my N value that I'm going to plug in here, is 13.6 divided by 16. And that's going to be 0.85 moles. And I'm going to take another pause right here. For folks to catch up all the way. Okay. Now my R value, 0.0821. So now what I'm going to do is I'm going to plug all this information in. Gives me T. 1.2 times 0.575. That ends up being 690. Nope, that's wrong because I did 1.2 times 0.575. How about that? 0.690. That makes more sense. Now what I'm going to do is I'm going to say 0.85 times 0.0821. That gives me 0.0697. So 0.690 divided by 0.6906975 gives me a temperature that is 9.89 Kelvin. Now, it's always kind of tricky to look at this and be like, is that right? I don't know. Those numbers are super small. Did I do all this right? And provided that you can go back and say, I put these numbers in the right location, I feel good about this. Do the calculation again so then you can confirm, yes, I plugged it in properly. Okay. How come we did not have to mess with with anything after? If you're asking about the units, um, the reason is because I just didn't include them. Um, I like to include them whenever I'm emphasizing like, hey, this is where everything's coming from. This is where everything cancels out. The units are still there, but that's. I hope that answers your question. If not, let me know. Okay. So does that all sound all right? Okay. Now what I'm going to do is I'm going to get another new slide real quick. And I'm going to say you have P1 V1 over T1 equals P2 V2 over T2. You have 3.2 liters of a gas at a pressure 1.7 atmospheres. The temperature is 390 Kelvin. And the temperature increases 30 degrees, which 30 degrees is the same as 30 Kelvin. And the pressure goes up 5 atmospheres. What is the new volume? Okay. So this is sort of like that. I think it was option B or question B. The temperature increase, what's that going to do to the volume? It's going to cause the volume to go up. The pressure increase, that's going to cause the volume to go down. So those are two things that are in conflict with one another. The temperature goes up, which should cause the volume to go down, but the pressure goes up, the temperature goes up, so the volume should go up. Therefore, what happens to the pressure? What happens to the volume? So we're going to plug all this in. 3.2. I'm going to write to the left of this my initial pressure, 1.7. And then my T1, which is 390 Kelvin. That's equal to, well, my P2. P2 is where my pressure has gone. It's gone from 1.72, it goes up 5, so it goes up. It doesn't go up to 5 atmospheres, it goes up 5 atmospheres, so 6.7 atmospheres. V2, that is what we're trying to solve for. And then my new temperature is 420 Kelvin. So there we go. So 1.7 times 3.2 divided by 390 gives me 0.013948 equals 6.7 V2 over 420. And multiply each side by 420, and you get 5.858 equals 6.7 V2. Divide each side by 6.7, divide each side by 6.7. And you end up with your volume, V2, equals 0.874 liters. So that gives us, well, what is the overall change? Overall change is that our volume drops. Okay. Now, the very last slide, the reason that I felt like everyone could depart if they wanted to is this last slide is just a summary. Takes all of those equations, Boyle's, Charles, Gay-Lussac, and Avogadro's law, and then shows where we end up with those with respect to the combined gas law and the ideal gas law. That's what I got for today. On Monday, we're going to be breaking into some new stuff, or we're going to be starting some new stuff. I hope you guys have a great weekend. If you've got any questions, let me know. I've got office hours starting at 12:30. Other than that, though, I hope you have a great day. And thanks for hanging around. I hope that I was able to answer some questions and clear up any confusion. Absolutely. And go back one slide. Great work, everyone.